Let's look at logical sufficiency. The following sets of logic elements are sufficient to create any logic function. We've already seen that and, or, and not comprise a sufficient set of logic functions for creating any logical function. But now we can establish that there are some other sets of elements that are sufficient as well. So are there any? Yes, there are. Let's see. There would be NAND gates, right? A NAND gate, so if you have a NAND gate, I can produce, with the NAND gate, I can produce oops, put these two, let's do this. With the NAND gate, I can produce a NOT by tying the two inputs together. I can then take a NAND gate and add that NOT after it, and this would produce an AND gate. And then finally, we saw that A plus B by De Morgan's theorem, right? Not the inverse of the sum is the product of the inverses. So what we can do is we can take an AND, and we're going to get rid of that, or double bar that. So we have NOT, and then we just simply need to invert the two inputs, and this will get us our OR. So a NAND gate is sufficient to produce any logic function because we can create the three logic functions of AND, OR, and NOT. You can do the same thing for NOR, so I won't do it here. Let's go to the next slide. I think we show what those are. So here we go. For the NANDs, we have the inverter, we have the AND gate, and we have the OR gate like I showed. And for the NOR, we'll have the same thing. You put the two inputs tied together and you'll get an inversion. You can get an OR gate, and here you get an AND gate. Let's look at implementing a Boolean expression. Implementing a logic or Boolean expression is really quite simple. Here we'll show it by example. So we have a function f that's equal to this expression in 3 or 4 inputs, actually, A, B, C, and D. And the functions, the elementary functions or operations that are involved in this expression are just the ANDing, the ORing, and the inverting. And so we can implement this using our AND, OR, and NOT gates. Now what we'll do is we look at the most outer, the most outer operation, okay? We have 3 terms that we're going to OR together. Okay, and so that means that we need to have an OR gate here, and we have 1, 2, 3 inputs. 1, 2, 3 terms that will feed those 3 inputs. Then we look inside each of those terms. So for term 1, we have the product of A with B naught and with C. So that means we're going to have an AND gate. So this, I'll say this is 4, and this is going to be implemented here with this AND gate. And we're going to AND A and C, and then the not B. So this gives us not B right here. For the second term, it's just ANDing A, B, and C. So that's straight up here. We got an AND gate, call this 5. So here's that AND gate. We're going to AND A, B, and C. For the last term, that's actually comprised of ANDing 2 terms. We have, let's say we'll call this 6. We'll call this 7. So here, this output is 6, and this output here is going to be 7. And those two are ANDed together in this AND gate here. And then the inputs for our 2 ORs are going to be C and D, and then D naught and E. And here we have an inversion of D to get D naught. So it's pretty straightforward. You start from the outside, the most outer operations, and move to the inside.